PVS has been available since 1993, stands for Prototype Verification System, although initially it was actually People's Verification System because NSA owned the previous system and we couldn't give it to people, we couldn't publish papers, we couldn't do much of anything with it. So SRI created their own, paid for this. It's interactive theorem prover, like Coq, like most of these. Has hundreds, maybe thousands of users. We don't try to track them or anything. It is open source. Current version is 8.0, has Emacs and VS Code IDEs, just like Coq. I use the Emacs because I've been Emacs user since 40 years, something. I never got used to VS Code. But, so it has a lot of components. It's got a parser and type checker. It's got the prover. The prover uses the Shostak decision procedure, but also you can invoke Yikes, either version, because there is slight differences between Yikes 1 and Yikes 2. And it has many NASA extensions. So we've been working for many years with NASA closely. In fact, I have regular meetings with the NASA people who have made all kinds of extensions and mostly made the mathematical libraries that NASA actually provides. It has a ground evaluator, both to Lisp at the moment, but it also has a PVS to C and a PVS to Rust capability. I won't go into those. It has a model checker underneath. It has WS1S underneath. That's like a set theory, simplified set theoretic decision procedure. As I said, it has IDs and it has extensions such as Meta-Tarski, Bernstein polynomials that NASA provided for this stuff. It actually features, if you know the movie The Martian, there's one point where there's a bunch of code flashing by the screen. It turns out that's a NASA library code that's flashing. So it's based on higher order logic, like most of these others, Lean, Coq, all of these are higher order logic. It is a classical logic as opposed to a constructive logic. It's in some ways that makes it easier for new users to kind of understand what's going on. And also it has a set theoretic semantics because of that. That also in some ways makes it easier to understand. So it's kind of type theory with set theory underneath each type in a sense. Because it does have predicate subtypes. For a long time, that was one of the key features. And as talking to Shankar just recently, I rarely write a spec that doesn't use predicate subtypes overall. This does make type checking undecidable. But what happens is that it just spits out a bunch of proof obligations. And you can prove them whenever you want. You can prove them right then when you see them. Or you can say, that looks okay, I'll prove it later. I want to get on to the real lemma that I'm actually interested in, that sort of thing. One thing I should say, we were always geared more towards what NASA and various other things needed. So it's more like applied math that in some sense, although to build up to applied math, you often need actual mathematics underneath. So the NASA library can be divided into the pure mathematical side and the kind of collision avoidance stuff and various things about floating point, all that sort of thing is not very interesting to pure mathematicians, but you do run into it in real systems. Let me stop here and just show you. Okay, so this is a definition of an ordered binary tree. So it starts with a data type defining what an ordered binary tree is. Actually, it's just defining a binary tree. The ordered binary tree would be a subtype of that type. So you have the usual thing. You have a leaf. You have a node that has a value in it, and a left tree and a right tree. And then the second theory imports that theory, but now it's going to give you an ordered binary tree based on a less than or equal, which is just some total order on some type. So this can be any type, any total order for that type. So those are theory parameters, as they're called in PVS. The only place you can put types, essentially, is on theory parameter, on theories, or on local declarations can have their own type parameters as well. So, so this is an ordered binary tree. We define what ordered means. It's a pretty obvious definition. Every function in PVS has to be total, although because you have subtyping, you can specify what the domain is very precisely, or the range, etc. But they're all there's no partial functions in the direct sense. So we have to give a measure here to say that this ordered function is well defined. And all that happens is the measure is applied to, in this case, the system knows that when you say size, you mean that the size is what's decreasing with each recursive call. And then it defines what it means to insert. And then the lemma I'm going to try to prove is that ordered of insert step, ordered insert. So ordered insert step just says that when you insert after you've already, what does this say? This is actually a induction scheme in effect. So for any property of X, if every PP of A implies, then you can say that every PP of insert X into A. So it's just an inductive step. And in PVS, you can induct over things and say, oh, I want to use this inductive rule that I've defined. So you can define your own inductions in effect. And then ordered insert is what I'll show the proof of. So this is all in Emacs again. One of the problems I have with so you put the cursor where the proof is, the thing you want to prove is, and then you do medx. Oops, medx. X. Prove. Type checking. Oops, type error. Oh, I know what's going on. Okay. So you can just type check like that. Okay, so now it says that it's type checked. And if I go back to the ordered insert, Alt-X, PR. No, I don't want to rerun the existing proof. Okay, this uses Gensen sequent calculus, basically. So what you have is hypotheses above the line and goals, possibly 0 to any number below the line. And what you're trying to prove is that the conjunction of the hypotheses implies the disjunction of the conclusion. So one thing I can do is show proof. Let me do this over again, because I wanted to show the actual proof. No. That's good. You can run a step proof. This takes an existing proof and shows it at the same time. So this is the proof that it already has. Now, this is not a proof in the sense of, this is a proof script, you would say, rather than, So what it's saying is that first we're going to induct and simplify over A. Now A here is over binary trees, so we're using the data type induction scheme for this when we do that induct. Now you can just do induct by itself and then over A, and then it would just do the simple induction. But here it's saying and simplify, which usually takes care of the simple parts for you. And in addition, we're saying, okay, and also rewrite with ordered insert step. Use that, that ordered insert step that was there before as a lemma, essentially. Bring it in as a hypothesis, and then rewrite with it. So if I do just tab 1, it does that induct and simplify. And you see it rewrites with a bunch of stuff because the simplify part says, oh, and by the way, expand all non-recursive definitions. It actually will expand recursive ones too, as long as it knows that it's not getting in an infinite loop. It's got a fairly simple test for that. And then here there's just still one subgoal, but now you see there's a whole bunch of hypotheses and two goals. Now if we do rewrite with ordered insert step, I don't know why it needs it a second time. Oh, and you see the square brackets and the set braces. The set brace shows which formula is different from the previous sequence. So you can see that this is what's new from that the rewrite. And you get some information as it's doing these commands. Many of them will tell you what it's doing as it goes along. And then if we do tab 1, we're bringing, okay, type reg less than or equal. What this is it's saying that I want to bring in directly in the fact that this less than or equal is a total order over RT. I want to bring that fact in. Type pred is a way of letting you bring in the subtype predicates that are involved in a type. This was a subtype predicate. You have to, the system is very careful about how you can use the subtype predicates. If you bring them all in, you just get swamped with stuff. So you bring them in as you need them, basically. Then grind is kind of throw the kitchen sink at it. It's what do you call it in these other systems? Hammer, or so it's the equivalent of these hammer kinds of things. And that just finishes the proof. If I go back to this, to the PVS thing, it says, okay, rewriting with all these things, and then trying repeated scolomization, instantiation, and lifting, and then QED, and all of this uses the Shostak decision procedure underneath. So you can think of that as integer linear arithmetic. Decision procedure, because that's what it is, in effect. Any questions on any of this? Okay, I'll go back to, I don't know how much time I have.
10 minutes.
Okay. Let me go back to the slides then. So, it has a rich type system. Most of these systems have these basic things: enumeration types, basic types, function, record, tuple, and co-tuple types. And that's the syntax for them. It has recursive types. You saw this for the binary trees, and list is one thing. It has a pretty extensive prelude with some 1,000+ lemmas in there, and develops finite set theory and much of the properties you need for real numbers versus natural numbers versus integers. One thing that PVS does that might be a little different from many systems is that it has a notion of number kind of at the top, and then it has a number field underneath that, which allows you to define star times plus divide, etc. And then underneath that it has ordered field, which adds the less than or equal, etc. And then under that you have reals. This gives you room to basically put other things in between. So you can define complex numbers as between the number, or actually you would do number field and reals. It sits in between. And then you can view reals as a subtype of complex, as most mathematicians tend to view it anyway. And there's no such thing, there's only one zero, for instance. There's no, oh, this is zero integer as opposed to the zero for the reals as opposed to the zero for whatever. You just have that one integer. And then it does have co-data types or co-algebras, depending on how you look at it. It looks, the syntax is very similar to the syntax, but it expands to a co-algebra, so you get by simulation instead of induction schemas and that sort of thing. We also extended the data type mechanism with subtypes. But let me know when I'm getting close to the end. So with subtypes, so for instance, you can define, this is lambda, typed lambda calculus. And it has terms and types. And those are subtypes of this expression data type. And then you can say that the base type is a type, a function type is a type, but a variable is a term, and a number is a term, and a lambda takes a variable and a type, and an expression generates a term, that sort of thing you can say. So it gives you a way of getting in a grammar through the data type mechanism.
5 minutes.
Okay. And then this is one of the more important things about PVS. It has, the top one is the most important, predicate subtypes. So for instance, x colon real such that x not equal to 0, that is when you define division, when division is defined in PVS in the prelude, it's defined so that the second argument has to satisfy that. And then you get subtype TCCs that say, oh, you know, prove, usually it ends up being a proof of y not equal to 0 implies y not equal to 0, and you don't see those TCCs, they're simplified away even during type checking. But it often shows you where something goes wrong because you've forgotten to take the case that y might be equal to 0. And this is why it's good to at least examine the TCCs, if not prove them right away, to see that they're right.
What is a TCC?
TCC is a proof obligation. It stands for type correctness condition, and it's a proof obligation that PVS spits out. And that's what makes the type checking itself finishes. That part's decidable, but it's dependent on the TCCs that are generated, which may or may not be provable. Thank you for pointing that out. It also has dependent types, so you can do function types, tuple types, record types, and data types can all have dependencies in them. So it's pretty obvious, but these are dependent, these are more like term dependence rather than type dependence in some sense. So what you're doing, it's again making use of the predicate subtype capability. So, and then there's things like finite sequences has a n colon nat and then a below n arrow, the type you're interested in. And that's how it does it's a dependent type then. And it's kind of like an array that includes its dimension. The expressions are all pretty much straightforward, what you expect. There's coercions are kind of, no, coercions aren't the interesting one. Yeah, no, this is all pretty much what you expect. There is a tables in PVS. This was actually used on the FDiv problem. You'd give a partial table and you'd say don't care in various places, basically by leaving them blank. And then when you took the original FDiv specification, you would find that one of the things that was left blank actually mattered. You did care what that value was. It wasn't a don't care. And the TCC, the obligation that came out of this showed that. But you know, lots of systems tackled that as soon as it came out. I'm not saying PVS was the only, but we all jumped on that as soon as we saw the FDiv problem. So you can declare a bunch of stuff. Most of these are what you'd expect: types, constants, recursive definitions, inductive and co-inductive definitions are there, formulas and axioms. You can create assumptions on the formal parameters so that if you call it with something, you'll have to show that those assumptions hold. So if you, I tend not to use this. You can usually push everything into the subtyping on the formal parameters, and you don't need that. So in the one I showed, you could, for instance, say that the total ordering you could put as an assumption rather than put it in a subtype thing. It has judgments. What those do essentially is you prove in one place that if like a closure judgment, nat plus nat is nat, you put that in one place, and now you don't have to prove those TCCs anymore. It already knows that fact. So this is a way of linking those to the type checker, so it knows, and to the prover, so it knows, I don't have to prove nat plus nat is nat. I already know that by the judgment, and you do have to prove the judgment, of course, but once you prove that judgment, all the TCCs that are instances of that are automatically proved. Conversions is a way you can say that a constant from one type to a different type, I want to use that as an automatic conversion. So if the type checker would otherwise fail, see if it can apply this conversion. And if it can, then it just says, that conversion is applied, and it'll just apply it and then go on. And that's often very useful. I don't know how much time I have, there's a special thing called lambda conversion that I don't think any other system has, that essentially lets you do things like do state of a state type, and then say, this is a state type over int, and I want to add that variable of type int to 0 or to 1 or something. Then it'll automatically do the kind of lambda lifting of things so that makes sense. That's a nice one. You can give auto rewrites in the specification itself. You can say, then after this I want these auto rewrites to be available, and then when you start the proof, it just looks for all those auto rewrites and throws them in. And declarations may have local formal parameters, since we don't have a way of doing pi or sigma types. Because you lose set theoretic semantics if you do that. But with the local parameters, you can at least define group, and then define group homomorphisms without having to declare a second theory that has now 2 types for the groups. And then you want to say that homomorphisms are transitive. Well, now you need a third theory. So this allows you to not have to do all that. You just put as many local parameters as you need in there. And I'll just do one more slide at the end. There's lots here. I'm happy so NASA has a bunch of libraries. This is the starting list of their mathematics libraries. It continues, and then I separated out the application libraries. So these are these are the current ones in their NASA Lib version 8 that you can get. Their library is all on GitHub, so you can get that, and you can go to pvs.csl.sri.com and get pointers to this stuff. So, and there's more of those. And we have many applications going back to many, many years. I won't go through those, just giving it. Have been courses. I think there's a couple even currently, but I don't remember the details. Have a lot of future stuff. And this, if you want to run PVS yourself, this tells you how. The VS Code version works, kind of. NASA is in charge of that. But if you go to PVS, you can either go to the PVS plugin, you have to get to the PVS 8 branch, but then you can, the VS Code will download automatically the stuff you need to get up and running. You grab that Visix, if you know what a V6 or Visix, I don't know how it's pronounced. Or if you like Emacs, it's a little simpler to install. So that's about it.
Thank you very much.